Okay, so we'll be talking about invariance still in this lecture, and in particular about connectivity invariance. So I told you what connected means last time. So a graph is connected if between any two vertices there exists in this graph a path from one to the other. And we need another fundamental notion. So this is an indication of the entire graph. So there may be some vertices here and maybe some edges, right? And this indicates a separation of the graph. So what is a separation? A separation is an unordered pair of two sets of vertices which together make up the entire set of vertices, but not necessarily disjointly. So they don't have to partition the vertex set. They may overlap with the property that from A minus B to B minus A, there's no edge. Okay? Put another way, a separation of a graph is a set of two sets of vertices such that every vertex of G is in at least one of them, and all the edges of G are induced by one or the other of these two sets of vertices, possibly by both. So this edge here would be induced by A, and it will also be induced by B. This edge here is induced only by B. This edge also is induced only by B, although this vertex also lies in A. Okay? Questions? That's a separation. So that's a separation of G. The main thing is there's no edge in G from A minus B to B minus A. That's the important thing here for the definition of a separation. And this separation has order K if there are K vertices in this intersection. Right? So a K separation of G is a separation of order K, which just means that A intersect B has K elements, K vertices. Right? That's a K separation. Okay, and now we call G K connected. For an integer K. If what? If there is no proper separation of order less than K, and the separation is proper if A minus B and B minus A are both non-empty, right? For a separation itself, as such, we do allow that A is a subset of B or B is a subset of A, in which case, of course, the bigger one has to be in the entire vertex set. That is allowed in general, but not very interesting. So normally, we consider proper separations where A minus B and B minus A are both non-empty. So, and G is K connected if there's no proper separation of order less than K. Now, if K is 100 and our graph is a triangle, a K K3. That would satisfy this, right? So a K3 doesn't have a proper separation at all. A Kn, a complete graph on any number n of vertices, has no proper separation at all, because as soon as you have a vertex in A minus B and a vertex in B minus A, in a complete graph they're adjacent, but they're not allowed to be. Right? So complete graphs don't have proper separations, which means that every complete graph always satisfies this, no matter what K is. And that's a bit odd. There are also more fundamental reasons than being odd for us not wanting this to stand. So we add something, G is K connected if there's no separation of lower order, and G has more than K vertices. Okay, so that makes a little more sense. So a complete graph on 100 vertices would be 99 connected, but it would not be 100 connected. Okay, so for example, a triangle is 2 connected, it's not 3 connected, just for want of vertices. Okay, and so that's a kappa. Kappa of G is the largest integer, the biggest K, such that G is K connected. Okay, that's the connectivity of the graph G. The largest K for which G is K connected. Okay, questions? Right, now let's do the same thing for edges. G is L edge connected if, now this time we make no requirements on the order of G. We just say that for every set of edges of G, if this set has fewer than L edges, then, or I think I can write it below here. So if F has fewer than L elements, then G minus F is still connected. Right, and remember the notation G minus F when F is a set of edges is just the graph obtained from G by deleting these edges that are in F, but not deleting any vertices. Right, so if U is a set of vertices, then G minus U is the graph you obtain by deleting the vertices, and necessarily, in order to get a graph, the edges incident with vertices in U. But G minus F is just, has all the vertices of G and the edges that are not in F. Okay, so this is when G is called L edge connected. So lambda of G, which we call the edge connectivity of G, is just the analog of the above, is the largest L, such that G is L edge connected. Examples? Yeah, so here's a nice example. That's the octahedron. If you think you knew what an octahedron was, now you no longer do. This is the graph of the octahedron. If you imagine an octahedron in the way that you know it, then you can maybe see that this makes such a picture. So you can project it, if you turn it the right way, onto the board to give this picture. That's the octahedron. And in the octahedron, the connectivity and the edge connectivity are both 4. So connectivity is 4. Why? Well, it has at least 5 vertices. That's necessary. And there is no separation, no proper separation of order less than 4. So whenever I cover the vertex set by 2 sets A and B that overlap in at most 3 vertices, then I will necessarily have an edge from left to right if there are vertices on the left and on the right. Why? That's not easy. Right, you have to, yes?
The minimum degree of each vertex is, of the vertex set is 4. So
that's right. The min degree is 4, and we'll get to that in a moment. So the min degree is related to the connectivity. It's not quite that simple. But it is true that this vertex is separated by these 4 neighbors from that vertex. And therefore, this graph cannot be 5 connected. That's as much as we can say at this point. Yeah, very good. But we cannot quite say that it's, so it cannot be more highly connected than 4, but is it actually 4 connected? Well, you have to look at every separation of order less than 4 and so on, and there are lots of those, and then always find an edge from left to right and so on. It's a long, long process. Okay.
The image I have in my head is that I imagine that from each 2 vertices there are at least 4 different ways to go.
Oh, yeah, that's an image that you can dig out of your memory again when we get to Menger's theorem in chapter whatever it is. Yeah, well, that will come later. Okay, so, right, now let's take another copy of the octahedron. Yeah, okay, I'm going to use the same. So here, we're sharing these 2 vertices. Then this graph is still edge connected. So lambda is still 4. It cannot be 5. It cannot be bigger for the same reason. Just look at one vertex and you can delete its incident edges and take that as f. All right? So this is still 4 edge connected, but it's no longer 4 vertex connected, 4 connected. So the connectivity, in fact, is 2, right? There is no proper separation of order less than 2, 1 or 0. It has at least 3 vertices. So it is definitely 2 connected, but it's not 3 connected because there is a set of a separation of order less than 3, namely this. Okay? All right. So those are some examples to keep in mind. And what we have shown, or, well, not shown, but what this suggests is that these invariants are indeed related, and the fact that they are persuaded me to keep this headline for today's lecture. And this is proposition 142, proof of kappa less than lambda. Okay, so we have to show that we can separate a graph with at most as many vertices as we need edges to separate it with, sort of broadly. Okay, so let's start with a witness for this lambda. I'll tell you what witnesses are in just a moment. So let F be a set of edges that witnesses lambda. So what do I mean? Usually, or often, this word witness, so there is a notion in logic which is a precise mathematical term, witness, and I'm not using it officially in this technical sense, but informally I am using it in this technical sense. So whatever I use, you can probably make precise to mean exactly that. So informally, what does it mean? When you have an existential statement, there exists a blah, then any witness for that claim is any blah. Any blah is a witness for the claim that blahs exist. Any wolf is witnesses the fact, or witnesses the assertion that wolves exist. Very innocent use of the word witness, very appropriate use of the word witness. Now here, what is lambda? Lambda is not an existent statement, right? So it's a little trickier. And what I mean, of course, is the obvious thing. Let's take a set of edges from which you can easily see that the edge connectivity is lambda. So that will be a set of edges that does disconnect the graph. So it would have to be bigger than lambda, but not much bigger. It would have to be one bigger. So a set of edges that does disconnect the graph, and you can see in the graph that you can't disconnect the graph with fewer than order f many edges. That will be a witness. Okay? So, then G minus f has two components. That's a big jump. It's similar to the jump that you made earlier to carts. I'm claiming here that f is a cart. Let's do it properly. So if f does disconnect the graph, then after deleting f, you can't get from every vertex to every other vertex by a path anymore, right? So there exist two vertices between which G minus f contains no path. Let's take C as the set of vertices to which you can still get by a path, and C prime as those to which you can still get by a path from the other vertex, sorry, from this vertex and that vertex, between which there is no path in G minus f. And these obviously are not obviously, these are connected vertex sets, so the subgraphs they induce are connected. They're even maximally connected. There isn't a bigger connected set because that would still then be reachable from this vertex, and the definition I just used for C prime was everything you can reach from this vertex. So this is indeed a component of G minus f. So is that. Okay, so there are two different components, both non-empty. Components are always non-empty because they're connected, and connected graphs by decree are not empty. There may be one vertex only, but they are non-empty. Could there be any other component? No, there can't. Why not? Well, you can't have edges of f between more than two of these components because we could then delete some of those edges here, and we'd still have a disconnected graph. So a proper subset of F would still make, the deletion of a proper subset of F would still produce a disconnected graph. But since F witnesses lambda, there is no such proper subset. It's the smallest set of edges. It is a smallest set of edges, such that deleting it produces a disconnected graph. But there is no, a smallest such thing. Okay, so there are in fact exactly two components. If G is connected. Now, if G is disconnected, it may have lots of components, and then F would obviously be the empty set, right? And in that case, kappa and lambda would both be 0, and we'd be fine too. Okay, so we were assuming that that G is connected. Okay, then F, deleting F produces two components. And so in G, there are edges between the two components, and they're all in F. Maybe there are other edges in F, maybe this one. Actually, no, because that would be unnecessary. That would have a smaller subset that still disconnects the graph. Okay, so F is a cut, even a smallest cut, a bond, but that's undefined, don't worry about it. Okay, so what's the proof idea now? Well, the proof idea is to just look at the vertices on one side, the incident vertices, the vertices incident with edges in F in one of these two components, and take that as our vertex separator as the intersection of a separation. Right? And the idea would be that X is no bigger than F. Right? F has a certain number of edges. All the edges from left to right are in F. So how many vertices can be incident with sets with such vertices on the right? Well, no more than F has edges, because, for every vertex on the right, by definition, you have an edge in F, and maybe even more than one. So X seems to be smaller, necessarily smaller than F. So why can't we say, well, let's form the separation. This separation here. And we have found a separation of order less than cardinality of F, because there's no edge from left minus right to right minus left. There can't be an edge here because that edge would be an F. Right? I'm talking about G minus F. Okay, end of proof. I saw some critical faces, so you may now voice your criticism. There is still something missing or something wrong. Yes?
Doesn't the right side have to have any vertices?
That's right. Correct. So the argument was, well, how do we know that this vertex exists? Good point. If it does exist, then this separation is a proper separation, and we need a proper separation for the definition of connectivity. Yeah, so what if it doesn't exist? Okay. Let's look at that case. And so the case where every vertex is incident with F is done. Case 1, every vertex is incident with an edge in F. Whoops. That's the case we still have to do. Right? Every vertex is incident with an with F. We still have to do. So let's say there exists a vertex not incident with F. That case we have done. Not incident with F. Why? Well, we can choose this vertex first. And then look at G minus F. G minus F is disconnected. And as we saw earlier, it has exactly two components. This vertex that we started with isn't one of these components. And then this vertex is separated by these edges from those vertices. And the set X here separates this vertex from those vertices. And this set X here does not include V, because V is not incident with F. Right? So here we started with the components, and then we looked at the right-hand side at one of the two components, but that was unnecessary. So we can start with V and say, let's just look at any vertex not incident with F. It lives in one of the two components of G minus F, and then the edges across the two components have incident vertices in that component that contains F, and these incident vertices do not include F, and they form a separator X and give us a proper separation, this one and that one, of order at most F. And it's proper because these vertices exist here, because components are non-empty, and this vertex exists by assumption. Okay, so that's that case. What about the other case? Case 2. Every vertex of G is incident with F. Okay. Change of picture. We'll get back to this picture later, but let's do a different picture. Let's look at a vertex V. An arbitrary one, that's important, but let's look, for the time being, just look at some vertex V, and we know that it's incident with F, so what color should we give F? Green. Okay, so F is green, and V has some edges in F that it's incident with, at least one, and maybe it has some other edges as well. But the neighbors to which you get through these other edges will also have, are also incident with F by assumption. And now, here's a completely different idea for X. X, let's take the neighbors of V. Now, does that give us a proper separation? Well, the idea is, again, that we have a separation into which sets? Into V plus its neighbors, that's the set A, and all the other vertices, together with the blue vertices, that's B. And then there's no path from V to any of these other vertices that avoids, well, there's no edge from, yeah, and there's no path from V to any of these other vertices that avoids X, and therefore G minus X is disconnected. So that would take us home if it worked, and X had size at most order F. Now, same objection, are there any other vertices? Well, maybe not. So if not, then V is incident to all the other vertices in G. But remember I said we choose an arbitrary vertex V. So we can now use that and say, well, if that doesn't happen for every vertex, we choose one that isn't adjacent to everything else. I can still say, well, maybe it doesn't exist. Maybe every vertex is adjacent to every other vertex. Yeah, but that's easy now. Then we have a complete graph, and a complete graph, a Kn, has lambda what? The obvious answer is n minus 1. Checking that isn't entirely trivial. It can't be bigger than n minus 1, right? Because you can disconnect a vertex by the edges it sends to everything else. Yeah, no, you can. So, but if you delete fewer edges, you can't disconnect the graph. Takes a little bit of puzzling. Never mind. So lambda of Kn is n minus 1. Kappa of Kn is also n minus 1. By virtue of this, there are no proper separations of Kn. Right? But only graphs that are bigger than K are allowed to be K connected. So Kn is n minus 1 connected because it's just big enough and it's not n connected. Okay, so the connectivity of Kn is also n minus 1 like lambda, like the edge connectivity. So if there is no vertex that is not adjacent to everything else, we're done. If every vertex is adjacent to everything else, we're done. Okay, so there exists some other vertex that is not a neighbor of V. Okay, so let's use that separation. So what would that be like? It would be V here, then lots of blue vertices here, namely all the neighbors of V, and then some other vertices. Okay. Right, so that is a proper separation. That V doesn't send an edge to its non-neighbors, obviously. And so all we have to check is that X is no bigger than F. Is that the case? So we need that X has size at most F. Right, is that true? How do you prove that the cardinality of one set is at most the cardinality of another set? Old memories. Week 3 of your maths course or something. do you prove that? Does anyone remember? Well, you prove it by exhibiting an injective map from X to F. That's the definition of this line here. The definition of this line is there exists an injective map from X to F. Okay, let's find one. Okay, easy, I think. So all the elements of X are neighbors of V, maybe by an F edge, in which case we just map them to that edge. And that's certainly injective, right? Different neighbors of V are not adjacent to V by the same edge. And what about the other vertices? Well, they're also incident with edges in F. So we can just pick one of them and map them there. Right. Now, is that injective? Could this edge be one of those? No, because then this edge would go to V, but by assumption it doesn't. So is it injective? Could these two edges be the same? I mean, that's not quite so clear. Right? There might be an edge in F that's incident with these two vertices, in which case we might inadvertently or otherwise have mapped both these vertices to that same edge. Then it wouldn't be injective. Now let's get back to the original picture. G minus F has two components. V is in one of them. V is in one of them. So V is incident with some F edges and some other edges. Where do the other edges go? These other edges. Well, they can't cross, because then that would put them in F. So they have to lie in the same component here, these other neighbors. But then that edge wouldn't be an F. It would be unnecessary, because then a proper subset of F would still disconnect the graph. So as I said earlier, F does not join any two vertices in the same component of G minus F. Right? F really is a cut with sides, these two components. Okay, that was a little quirk at the end, which is sort of easy to overlook. Right? And prompts my exaltation that you really make sure your proofs are precise. It's so easy to claim something in graph theory that is completely false and you don't notice. All right? Okay. Yeah, this is now meant to be the correct and complete proof of that tiny little inequality here. Questions? No. Okay. Right. So how about the converse? Let me... How about the converse? We already know that we don't have a strict converse. We don't have equality up there, because kappa may be strictly less than lambda here. Here kappa is strictly less than lambda, so we shall not be able to prove that delta is at most kappa, or kappa is at least delta, right? But we might hope for something qualitative. So can we force kappa to be as large as we like by making delta big enough? So it's not going to be true that kappa is going to be at least as big as delta. It may be smaller than delta. But if we want kappa to be 1,000,000, is it enough to make delta 2 to 1,000,000? Okay, so question. Is there a function f such that for every k and every g, if delta of g is at least f of k, then kappa of g is at least k. What do you think? Can we make G k connected? That's what it means. Kappa is at least k, so can we make it k connected? By forcing the min degree up. Or not? Can you think of a graph of low connectivity, bounded connectivity, but unbounded min degree? Yes?
We have one vertex in the middle, and then we map it to a lot of other vertices,
Yeah.
and these are connected to
That's the middle.
yes. And then, I don't know, like I have 5 vertices over here.
Something like that. Right? Yes, correct. So every vertex has large degree. It leads to, I don't know, 99. But the connectivity is 1. You can even get the edge connectivity to be 1 as well by doing this. So this is anything of high connectivity. This is anything of high connectivity. Min degree, but the whole thing has connectivity and edge connectivity, only 1. Okay, so that's not true. Good. Can we do anything else? We can't do that. What did we do last time? Yeah?
I think you could still establish a relationship between the edge connectivity and the degree.
No, I just gave you this example here. So large min degree doesn't force the edge connectivity up. That was also 1.
What was that? Oh, yeah.
Yeah, but we could, yeah? That's right. We can ask whether large enough min degree forces a subgraph of high connectivity. Okay, so let me try to correct that. Is there a function such that if the min degree of G is at least f of k, that's fine, then there exists a subgraph of G such that the connectivity of that subgraph is at least k? Yeah. Yes. Yes, there is. And that's the next theorem. So, theorem 143. That's due to Wolfgang Marder. it's a lovely theorem which has a brilliant proof, by far the deepest theorem in chapter 1. It says basically that for every, it says this, so now, for every G and every K, if the average degree even, we're assuming less, of G is at least 4K, then there exists a K-connected H in G. Right? If you look it up in the book, the theorem there is a bit stronger, and the strengthening is technical and needed later, not in graph theory 1, it'll be needed in graph theory 2, so it's good to have there because it comes for free, but the gist of it is this. Right, so such a function f exists, and it's a linear function with slope 4. So very, very easy, very simple function, not fast growing at all. It has to be a function of k, right? Independent of g. But the theorem says that if the min degree, or indeed if the average degree, is at least f of k, where f of k is just 4k, then the desired h will exist. Okay. Questions about the statement? No. Okay. So let me give you the first proof, first false proof of this lecture. We just do induction. All right, so we look at G itself. If G is K-connected, then that's what we want. So we're taking a graph of average degree 4K, at least. All right, so if G itself is K-connected, we're done. If not, it has a separation of order, proper separation of order less than K. So let's look at the two sides. So this will be a proper separation of order less than K, and so let's look at what A induces in G and what B induces in G. Well, if one of them is K-connected, we're happy. If not, we just pick one of them and we carry on. So if this is not K-connected, well, then there's going to be a separation of order less than K. We split it, and then if one of the sides is K-connected, that's fine. If not, we'll just continue with one of the two sides. We'll just pick one. We'll keep going. And how can this stop? Well, it can stop only if we can't find such a separation. And if we can't find such a separation of order less than K, then obviously the graph we got to was K-connected. End of proof. If you don't see immediately what's wrong, that will make me exceedingly happy. Not because I'm vicious, but because it'll be good for you to discover later what was wrong. There's one thing that should worry you instantly, even if you don't see what's wrong. What should worry you? That we haven't used our premise. We never used in this proof that the graph has average degree at least 4K. Now that can't be good. So we might have started with G being a one-vertex graph, for example. And something about this proof must be wrong. And where's the error? Yes. Yeah, exactly. So if this graph isn't k-connected, we cannot deduce that there must be a proper separation of order less than k. That's one sufficient reason for not being k-connected, but there may be another, and the other may be that G doesn't have enough vertices. All right? So right up there. And this is one of the more profound reasons why we require G to have more than k vertices in order to call it k-connected. Otherwise, we couldn't have such statements. Okay, very good. Did everybody get that? Yeah. Okay, so that's wrong. Let's try something a little cleverer than that. So let the order of G be called n, and half the average degree, let's call that epsilon. So we might ask the same thing as we did last time when we ran aground with a proof attempt in trying to find a subgraph of large min degree. And then the solution was to say, okay, we make the graph smaller, but in such a way that we keep the assets that we have. So last time we wanted to find a subgraph of large min degree in any graph of large average degree, large enough average degree, which turned out to be only twice the min degree that we wanted to end up with. But the proof strategy was to say, okay, if this graph doesn't have min degree, what we want, make it a little smaller by deleting a vertex of low degree, such that deleting this vertex doesn't put us in a worse position than we are in now, namely that the average degree that we had doesn't go down. And we can try and do the same now. Let's call this G1 and this G2. So G1 is the subgraph of G induced by the left-hand side of some separation of order less than k, and G2 is that of the other side. And can it happen, or can we be sure, to put it positively, that one of these two sides maintains our asset? So is either epsilon 1 or epsilon 2 as big as the epsilon, the average degree divided by 2 that we started with? And that's all that we're assuming. We're assuming that G has large average degree for k. So we're assuming that epsilon of G is at least 2k. Then if G is not k-connected, can we find a separation of order less than k such that one of the two sides is as good as we started with, so that its epsilon is at least the original epsilon? Now, that's a bit better. So let's see how this works. So we're assuming that the number of edges of G is at least Cn. N is the number of vertices. C is a constant, which I'm promising is going to be 2k, right? We shall be proving that if the average degree is at least 4k, so if epsilon is at least 2k, then this H exists, and epsilon being at least 2k means that G has how many edges? Well, epsilon times n, right? At least 2k n edges. But let's imagine we're in the situation where we don't know that yet. So we're looking for some number of edges, constant times, or function C is a function of K, but independent of G. This is we'll end up with C being the constant function for, but we don't know that yet. Let's just see whether we can prove something, or whether we can make this approach work for some C of K, and then write that down at the end. Okay, so that's the approach now. So if G has at least that many edges, does it imply that for any separation of order less than K, I'm not writing that now, that G1 has at least Cn1 edges, or G2 has at least Cn2 edges. N1 and N2 are the number of vertices of the left and the right-hand side, respectively. Right, so that would be nice if we could prove that, and we might choose this separation in a way that suits us. We haven't used that yet. At this time, we're saying pick any proper separation of order less than K. Okay, so we would like to show that if that exists, then this holds or that holds, in which case we can apply induction and continue with that side, or just invoke induction and say, oh yeah, but we'll know it for all smaller g. Therefore, this side, say, if that's true, contains this h that we want, and then that h obviously is also a subgraph of g, and we're done. Okay. Well, so does that follow? Well, if not, then, well, then not. Then both these are false, and G2 has fewer than Cn2 edges, strictly fewer than Cn2 edges. Right, and now we want a contradiction. So how can we get a contradiction from both sides being small? Well, the only contradiction can be to our acid. And the acid is that G has lots of edges. So we want to show that if this holds, then G has at most, or has fewer than Cn edges. And then we want to say contradiction. Okay, so let's compute that. So how many edges does G have? Well, G is the union of G1 and G2. So this has at most size of G1 plus size of G2 many edges. Now G1 is less than Cn1. G2 is less than Cn2, so this is less than C times N1 plus N2. Okay, so far so good. Right, but that looks exceedingly false. Right? So that's clearly not true. C times N1 plus N2 is not at most Cn, because the sum of N1 and N2 is usually bigger than N. What is the sum of N1 and N2? It's the set of these vertices plus the set of those vertices. So it is all the vertices of G, but these are counted twice. All right, so in order to get a contradiction at the end of the day, we would need this to be at most that, but it isn't. That looks pretty bad. Now, when you get to such a point in a proof, what do you do? Option 1, throw your hands up in despair and go home and have an ice cream. Option 2, you might check whether in the proof attempt you made some assumptions or you lost something on the way. So maybe your proof attempt is incorrect and is not going to work, but the statement might still be true. If you find such a place where your proof attempt is not so good, then you might improve it at that point. If you're unable to find such a place, if your proof seems optimal all the way through, then maybe that leads you to a counterexample. So your statement might be false. So there is always a way to go on from such a breakdown. Good to know. Okay, can anyone see where the proof attempt is not so good? Well, here's a place. We were very generous with this inequality. All right, so we said G has no more edges than G1 and G2 together. Yes, obviously not. But this might actually be a lot smaller than this sum here, because this sum also counts the edges in the intersection twice. Okay? So maybe we can improve there. So if we look at this in more detail, we might improve it. So could it be that we can improve this a little bit here? Well, not in general, yeah?
No, if it's in general, I thought that we could just subtract the edges without G1. Oh, no.
Yes, that's right. Yeah, no, that's the idea. So we could subtract the edges on the intersection. Right? That's the idea. So how much are we gaining? How much can we subtract, at least? No idea. Because there might not be any edges on the intersection, in general. So we'd have to go all the way back to hunting this separation and saying that, well, if the graph isn't k-connected, then there is a proper separation, not just any old proper separation, but one where we have lots of edges on the intersection. Alternatively, it might be the case that what we're trying to prove is really false. So could it be that, at least for an arbitrary separation, neither side has epsilon, at least the original epsilon? Could that happen? The idea was, well, it can't happen because we have a certain edge density, right? Overall. And then if the left-hand side is less dense and the right-hand side is less dense, then they can't sort of combine to this density. But this points us to how this can in fact happen. So if you think about it from there a little bit, then you come up with this example. So what's epsilon? Epsilon, number of edges per vertex, is half. Right? Average degree is 1. Every vertex has degree 1. So epsilon is 2, is half. What's epsilon 1? It's 1 over 3. Right? 1 edge over 3 vertices. And that's also epsilon 2. So we're not maintaining our asset. Right? And the reason is precisely that this is not going to be wasteful here. There are no edges on the intersection which we threw away, which we disregarded. Oh. So what does one do then? Well, as I said, one attack would be to hunt for a special separation. And it looks difficult. Another attack would be to say, okay, we'll make C a really fast-growing function of K rather than 4. But wait a minute. We never used that C as constant 4. We did this for arbitrary C. C is just a function of K, so it has nothing to do with our G. So that's not going to help us at all. So we seem pretty stuck. And now comes in Marder, and he does something really, really ingenious. And that's something that is really worth knowing. If an induction proof you're trying to do fails, try proving something stronger. Why can that possibly work? Well, it can work because you also have a stronger induction hypothesis. Right? So, and in fact, it often worked like that. And it does work here as well. And here's the clever Marder way of dealing with this. We're assuming not that G has at least 2kn edges, but we're subtracting some constant b to be determined. We're assuming less. And we still want the same conclusion. We still want a subgraph H that is k-connected. Okay, now let's see how this change. I mean, this is ridiculous, right? We're just making our assumptions weaker. But look. Then here, we only need that, or we need that in order to say induction, to be home by induction, right? You're looking critical. No? Okay. So the claim now is that if G has at least this many edges for some b to be determined, b is going to be a number. Then there's this H that we want, a k-connected subgraph H. Well, if that's true for the left-hand side or for the right-hand side, we can say, yes, home by induction. If not, well, then we have this. But now, look at this. Then G is at most this plus that, but this plus that is this, minus 2b. And we want that to be less than the original number of edges there. And now suddenly we're in with a chance if b is big enough. Right? So which b are big enough? So that is going to be true and if that is less than b, then c times the overcount is at most b, so that's one of the two b's, and this remains. So that will be fine. So is that going to be true? Well, we know something about this. We know this is less than k. right? So if C times k minus 1 is less than B, then that is true. All right, this is at most k minus 1. Okay, so there are lots of ifs, but now we can try and nail the proof down. So define C as 2k, as promised, and B as whatever follows that makes this true. So let's take as B 2k times k minus 1. Right, then all this works, it all clicks into place, and we're done. Or are we? Still looks a bit magical. We need one final check. So I just wrote this. But there's something wrong with this argument, or with the argument that as soon as we have C and B satisfying this, everything works. And that is your parallel processor suggesting counterexamples all the time while you're reasoning. And the parallel processor would alert you to the fact that, well, maybe you could make this true by choosing C and B both 0. Then what would we have? We would claim that any graph that has more than 0 edges, or at least 0 edges, yeah, most graphs do, then it has a k-connected subgraph. Well, that's not quite so obviously true. If a graph has at least 0 edges, it has a k-connected subgraph, no matter what k was. So where's the mistake? Well, the mistake is that I just showed you the induction step, and I always said, yeah, and we say we're done by induction. But the induction does have to start. So start the induction. At G or N equals 2k. If you work it out, and you're assuming that G has 2k vertices and at least this many edges, you do have to do a few sums to work it out what it is, but it will tell you that G has more edges than the complete graph. That, in fact, gets you to to twice the number of edges, about twice the number of edges than the complete graph has. Okay, so what now? Are we really, really hopelessly stranded or not? Now here comes something really, really tricky, and use it with care. We're proving that if G has 2k vertices exactly, then this statement is true. Proof, if G has at least that many edges, but only 2k vertices, then the moon is made of green cheese, because such G's don't exist. So the statement is true. And it can indeed function as our induction base. Now that is really, really weird. And I invite you to read the proper proof in the book as it's written there. I used to go through the proof as it's written with the class and the lecture, and then at some point found that I lost everyone all the time. There are so many clever ideas in the proof which you don't understand unless you've seen this. This is something like that Mather must have gone through before he found his proof. And the proof is really wonderful. It has a similar induction start, which starts on the empty set. Do read it, please. And if you don't understand it, either ask me or ask in the exercise class. So I chose not to present it here and give you the motivation and the way of how to arrive at that proof instead. Right. That's it. That's meant to be correct now. Well, no, I haven't proved it. I just told you that I've sort of proved it, yeah.